Hi, my name is Jamie Saxon. I'm a Postdoctoral Fellow at the University of Chicago in the Center for Data and Computing. I'm going to describe a project that used GPS location data from smartphones to measure and characterize the local mobility networks of urban neighborhoods and the social relationships that those networks express. Because this is a spatial conference, I'm going to conclude with the talk with some strategies for ensuring that this sort of work is robust, including my current work on developing ground truths for measuring their representativeness. This project began with the incomparable Jane Jacobs, who wrote in The Death and Life of Great American Cities that if self-government in a place is to work, there must be a continuity of people who have forged neighborhood networks. These networks are a city's irreplaceable social capital. Elsewhere, Jacobs describes the intricate ballet of city streets and she writes about the need for continuous urban fabric and cross-use between neighborhoods. She argues wonderfully that physical design and spatial routines are both formative and expressive of social realities. She wasn't the first to use the word social capital back to back, but she was early and she was hugely influential. Jacobs' work on social capital was formalized by sociologists who constructed it as basically social closure, or mathematically the graph clustering coefficient. If I have two relationships, A and B, the question is whether they themselves are connected to each other. And this is important because it allows for the enforcement of social norms. So if I'm a jerk to A, B can fix me if A and B are themselves connected. And that basic topology goes back in time to the dawn of urban sociology all the way up through the present day. But despite the importance of this concept and its history, big data had never really been brought to bear with empirical routines, empirical networks among neighborhoods and their impact on social relations. And so, of course, that has all changed with GPS location data. And so what I'm going to do in this talk is construct neighborhood networks from cell phone location data. I'm going to characterize those networks with simple graph properties that are inspired by the ideas of social capital and also simple tools of geographic analysis like k-nearest neighbors to construct local relationships. And third, I'm going to argue that variation in these concepts matters. It matters because it's what we do with our physical bodies on a daily basis in our environments. It's our most basic experience of the world. And it's hugely correlated with class. So it's part of this matrix of poverty and privilege in urban environments. But this isn't just something that rich people buy. It isn't just a Baroque reconstruction of median household income using big data. This is a different concept. And the way that I'm going to try and argue with that is by showing that it provides independent information when we go to look at other social factors. And I'm going to look at crime in particular. And the hypothesis then is just that better mobility connections are associated with lower crime. This work recently came out in a paper in Environment and Planning in B. I'll drop the link. If you're not already familiar with GPS location data, basically each line of data consists of 4 rows: a unique identifier, a timestamp, a latitude, and a longitude. And we have to construct everything further that we try to do with those data from those 4 fields. So a little less than 1% of the data for 1 month for one supplier for Chicago looks like this. This is May 2017. And you immediately see the structure of the city. This is Chicago. The black area to the right is the lake. All the white lines are highways. You see the airports, O'Hare and Midway. The loop is the shining white area in the center. The north side is the richer space. The suburbs are off to the left or the west. And we have Hyde Park about halfway down the south side along the lake. And Hyde Park is where the University of Chicago is, and you'll see that it's an outlier in a lot of these analyses. Data processing is pretty intensive, starting from the raw data. We have to drop imprecise locations that don't have a solid GPS fix or permission for that. Don't consider that driving through a neighborhood from the freeway counts as a genuine interaction with that neighborhood. So I'm going to flag places that are within 10 meters of highways as defined by OpenStreetMaps, and I'll remove those from the analyses. And then I'll join locations to census tracts and impute the home location of each device as the modal tract at night. And thenceforward, each device basically gets one count, so it gets normalized down. If one device has lots of activity, it gets dropped. And we'll be proceeding with an analysis basically just at the tract level so that I don't have to consider the individual level data. And so from these data, I want to construct mobility as a network. And the question is, how much time do individuals spend in the neighborhoods around their place of residence? And so for each home neighborhood, there's a fraction of out-of-home time that is spent in each other neighborhood in the city. And if we project this just onto the proximate neighbors, it looks like this. And so on the left-hand side, you have the suburbs, and on the right-hand side, you have the city. And you can see that the relations with the immediate neighbors are different. Right? In the suburbs, it's harder to jump over 1 million people, and so you're more likely to interact with regions that are near your place of residence. Similarly for resources, right? In the city, you might jump over 3 census tracts to go to a gas station, where you're less likely to do that in the suburbs. But this simplistic view of just projecting census tract to census tract relations onto a nearest neighbors graph is ultimately pretty inadequate. And the reason is that census tracts have different populations. And so we need to be a little bit more careful. And so what I'm going to do is I'll construct 2 concepts. First, a local out degree. And the question here is, what fraction of my time is spent in the immediate vicinity of my home? But the vicinity is going to be defined as a fixed 40,000 person area around the home. And so it's basically summing up each of the connections, each of the local connections, up to a 40,000 person area, and then a weighted fraction for that last one that's going to be from 39.5 to 42, flat or something like that. And then on the other hand, we have the graph clustering coefficient, which asks if the places that I go to interact with each other. And again, we need to take into account that census tract populations are different and that my relationships may be stronger or weaker with different areas. And so the edges and the nodes on that graph are weighted, and the clustering coefficient needs to reflect that. So with these refinements, we can look at the local out degree. This is going to be a value that theoretically could scale from 0 to 1. And you see after the refinements that the picture remains largely the same. The suburbs are more related to their local neighbors, so they spend up to 40% of their time in the areas around their home, and it's lower in the city. But within the city, there's huge variation. So I pointed out the neighborhood of Hyde Park, and indeed you see that it's a pretty striking outlier down on the south side here. And on the north side, the colors are generally lighter. That is to say, the interactions are stronger with neighbors than on the south side, which traditionally has been poorer. Alternatively, we could look at the clustering coefficient, and here we see the same basic spatial pattern: higher values in the suburbs, higher values on the north side, and a clear outlier in the south side with the neighborhood of Hyde Park. Here, the clustering, I've taken the log because there's wide variation in the scale, and shifted it to 0. Now, if you're familiar with the geography of Chicago, you'll already see in these maps basically a map of class of the city. But if you're not familiar with Chicago, it looks like this. Here, I've just constructed a composite socioeconomic status based on a principal component analysis, and purple is high, and if I flip back and forth between these, you really see that these are lining up pretty accurately. And so we can look at this again as a scatter plot, and there's really strong relationships between the clustering or the local out degree and class. And so here I'm showing the educational attainment of the adult population, and over 80% of the variance is predicted by the log clustering. Now, this is kind of interesting because earlier work by people like Eagle et al. Had found that higher geographic network diversity was associated with higher social class. And we can reconcile that contradiction both on the local nature of this analysis and also on the explicit prior about local spaces. It's not just a bunch of random ties, it's are you tied to the spaces immediately around you. Other early work also shows that there's a relationship between geographic ties and social class, And so what I really want to do is go beyond this and ask, beyond a link between mobility and class, is there new independent explanatory power for these new constructed variables? And there's a multitude of contexts where we would expect that to be the case, and I'm going to choose off just one of them, which is criminality. And so here you have log crime on the y-axis, and you can see that there's relationships for different income levels in Chicago for lower income areas, right? There's this interesting relationship, and I want to tease that out. And I'm going to do that using a spatial error model for logged crime. And if you're not familiar with it, no fear. It's basically like OLS, except we're accounting for the fact that there are correlations amongst the observations in our data set. And so I will control for routine activities. This is basically taking into account the populations of the spaces, the people who are at risk to be victimized or perpetrate a crime. So there's more crime in Manhattan because there are more people in Manhattan. So it's very simple. And social disorganization, so the social characteristics of the space. And what I want to see is, can I add these new mobility variables into this model, and do they add new information? And so the hypothesis is that higher levels of cohesion in the mobility networks are going to be associated with lower levels of criminality. And that is indeed what we see. It's going to be, I guess, hard to read these parameters, but they're negative and quite significantly so. And indeed, the information criterion is going to drop. So the model is better off for having added this new information about the mobility networks into the model for criminality. And this is highly robust to modifications of how we define disadvantage, how we change the modeling, the weights, the estimation methods, and so forth. But this is not a causal analysis. And indeed, I think it's just as likely that crime is depressing the use of space as that social capital as expressed through physical routines is depressing crime. So there's a great quote from Robert Snyder that in Washington Heights, as crime was falling, as elsewhere, residents stepped out of their homes, reclaimed parks and sidewalks, and overcame the fear that had driven so many people indoors during the years of high crime. And so what we see is crime had driven people indoors, crime reduced the use of space, but there was a social capital, there was an active reclaiming of space that pushed out the crime. And so these forces are opposed to each other and are both, I think, causal. So I also want to assess the robustness of this whole story. And in social sciences, generally would throw lots of covariates in and do the analysis lots of different ways. But with these GPS location data, I think we want to think about this a little bit more, right? So one of the big questions is how we construct the sample. And one of the things that you can do, right, is you have lots of data and you can make different requirements of what it takes for a device to enter into the sample. You can require a different number of nights. You can require different total volume of locations recorded. And you can manipulate and clean the data in different ways. And so what I've done here is I've used the nominal sample, a changed deduplication strategy, and a restricted sample that required more nights and more data. And you see that you get very consistent results on the key estimates for each of these. Alternatively, we could look at the just volume of data that was getting generated in various census tracts, and this has very little effect. So just artifacts of the data production process don't really seem to be affecting our results. And simpler constructions of the variables that we could get from the census, like what fraction of people walk to work or how long are commutes, those don't really change the story either. But that leaves a broader question of representativeness. And I want to clarify, right, that effectively we've stratified the data set by census tract. And so there's only so unrepresentative that the data can be. But we can look across the whole city and get a sense of who is in the data. And so we can do this by looking at characteristics of census tracts and weighting histograms of those characteristics either by the population resident in those census tracts or by the population of devices that we assign as living there. And what we see is that the device population is higher income, somewhat more educated, but these biases are quite moderate, and I would say I was quite impressed with how representative the data really are. This is also quite consistent with what we see from the Pew Research Center reports on mobile device penetration. But this reflects device residence rather than activities. And you would imagine that for a single fixed activity, right, the scale factor, the amount of data per person, would bear a fixed ratio. But different types of activities can happen in the same spaces. So, for example, commuters and tourists might visit the same restaurants and highways, but use their phones differently in those locations. And people biking in parks might have their phone out less than people who are partying in the park. So my interest is in coming up with lots of different count data that we can compare to GPS location data to assess representativeness. So things like payments. We can get a transaction, number of transactions, and number of people who came into the store. Stuart Lin, when he started working at this with these data at Cardo, looked at baseball games, and for which we have known attendance records. Advanced traffic management systems allow us to get red light cameras and toll counts. We can compare those to flows that we would construct through the GPS data. And computer vision allows us to get counts in small public spaces. So that begins to address the representativeness question. But there's other questions about how space is shared and how it can be optimized that I also am interested in. So social science research, right, on the use of space. How are we navigating the space with respect to other people? The GPS data are actually fairly sparse when it comes to individual locations at a given moment. And so we want other techniques for that. If we're considering the refinement of an existing single public space for the evaluation management of that space, we need more data for that individual space. So things like park closures and coronavirus times, or art in the park, is that stimulating use in happier times? And for that, computer vision should do the trick. And so I'm certainly not the first to have had this idea. Holly White, who sponsored Jane Jacobs' work in the first place, famously did the social life of small urban spaces using cameras. And people more recently have had the same idea. Placemeter ran from 2012 to 2016 before being acquired by Netgear. They used public cameras. Sarah Williams and the Civic Design Lab at MIT have done similar things in their benchmark project. SWA, an architecture group, did similar things in public plazas, and Unicast, GPS location, have married that with Sensormatic, which has counts of shoppers in stores. And so they're doing this exact marriage that interests me. So I'm not the first, and I certainly won't be the last to play with these data, but I hope it's interesting to consider how to do this. So what I'm trying to do is live detection and tracking from a network camera at full rate on lightweight hardware. And the reason to do this is that we don't have to bring in all of the video, and we don't have to deal with so many of the privacy concerns because the data only exists ephemerally. To do this, we can use a process called knowledge distillation, where we're taking an expensive model, running it on a fancy GPU to create the training sample that we use to tune a much smaller and cheaper model that can run at the edge. And for this, I simply have two of these models. And that gives us object detections on a frame. Now we need to go from detections on a frame back to GPS data. And to do that, all we have to do is tag control points in an image to GPS coordinates, and then we can construct the homography, which is just a matrix projection from the image plane to the GPS plane, or the local coordinate reference system. And hopefully you can see here in this film that this looks a lot like the maps that Holly White made of the Seagram's Plaza, where he has counts of people over time. And you can do the same thing of any public camera in the city. Of course, this is a low enough rate that you couldn't do tracking on it. If we look towards the tracking, we can, of course, get entrances and exits from public parks. If we watch for bicyclists, we can see different uses of the space, which is important to me. From the counts, we can compare that to the GPS location data by time of day and by activity that people are partaking in. We can look at entrances and exits, and we can see cute things like spontaneous formation of lanes going in. So in summary of this project, I characterized the human mobility in Chicago neighborhoods using clustering coefficient and nearest neighbors interactions, closely inspired by Jane Jacobs' work and by methods in geographic analysis. And we saw that mobility is strongly correlated and indeed, I think, is a component of class. Consistent with the existing theories, it also has independent and predictive power for crime with the correct sign. In my ongoing work, I'm excited by the potential of GPS data, which have unique strengths in their scalability and ability to capture activity between geographies. And I've found that the data are surprisingly representative, to me at least, of the population. Notwithstanding, continued work is needed to assess the biases to apply these data to planning decisions. And because the data are fairly sparse, complementary techniques like computer vision are needed or are useful in measuring and optimizing individual resources. Spatial routines usually express some sort of a social or economic routine, but computer vision can help us to disentangle these even further. Thank you.
Jamie, thank you so much for joining that presentation. We have a question in the chat, actually, from Javier, who is asking, is it possible to do this directly on the camera on the edge to handle privacy issues?
Yeah, this is an awesome question. And the answer, I mean, the first answer I wrote is, yep, it's possible. Now, directly on the camera, we can be a little bit more precise about that. You can buy a camera, if you buy a Hikvision camera, they have a certain amount of, increasingly, they have a certain amount of machine learning built into them. And my experience is that it's great, but it's usually not quite adequate to do something like mapping trajectories. You'll get person detections. But in small situations, the models they're not quite accurate enough to do continuous tracking. And they're going to have variable performance by time of day. So yes, out of the box commercial things do work. I have focused on doing this, as I said, on lightweight hardware. I guess I don't have a bunch of it is at home now because everything's shut down. But yeah, it'll run. Oh, I have one of these guys. So it'll run on a device like this. This is just a Google TPU Coral accelerator, or you can get the dev boards directly. So you do need something that will do the machine learning more efficiently at the edge. The Raspberry Pi on its own can't quite do it. But certainly you can have edge devices that go directly through the network camera, do all of the processing, convert all of that into streams of data, of trajectories, of person counts, and so forth, of use of space. They can do all the projection, all of that live, and a $100 Raspberry Pi can do that. So yeah, the answer is certainly yes, and the privacy thing is key. Now there's like a little caveat to that, right? Which is that you need to ensure the data quality somehow, and you need to train the model in the first place. And so you do need to take a certain amount of the data off in order to check, or you need to be running 10 minutes of data every day at different times and under different conditions. And so like, person tracking is pretty easy if there's only one person in the frame. If there's 12 people in the frame, it starts breaking down because everyone is occluding everybody else. And so you do need to take enough data off to validate it and to make sure that you're comfortable with the performance you're getting. And you can also do that by marrying it with other types of sensors. And of course, all of those sensors themselves have limitations, right? So like if you have a passive infrared or a sonar, right? Those are going to get counts of activity, but it's not going to be able to separate a couple walking side by side. And so as long as you construct like variables, right? There's activity at this moment, and I see a sonar count at that moment. That gives you means for doing some of this validation. But yes, and the answer is yes. You do need to do a lot of reduction of the models from large ones to ones that fit on this type of device. But if you do reduce the models, you can get high enough accuracy at the edge.
Awesome. Okay, we've got another question here from Guilherme Zagatti. who is asking, with regards to the last part, how did you get started with movement tracking using machine learning? Any good pointers or tutorials?
Oh, wow. This is, so the way I got started was by thinking that it couldn't possibly be that difficult. And so Luke Anselin, who's the director of the Center for Spatial Data Science, basically kept pushing back on work that I was doing with cell phone data. And he's saying, how do you know that this is reliable? And I was like, oh, well, I'm sure I can just look at a camera. And so I got started in it through a great store of overconfidence, and then sort of just kept on pushing. I don't know that I would recommend any particular. There's a lot of books out there. I'll try to drop some links after, but basically you just have to do it. You have to get a camera up, playing, like I have cameras up in my office so that I can track myself. I can move through it. I have like 12 different cameras in different places. And you have to play with it. And some things work and some things don't. I thought 3D tracking was going to be super important, and I spent like a month on it and it didn't work. But I think there's another part to that question, right? Which is that, how do you find the time? And it's great for me because I'm in an academic institution. I sort of decided that this mattered and I was going to focus time on it. And I think a lot of people here are in industrial settings. And so there's a continual problem for developing skills that the company needs to see that there's value in it for them to invest in your human capital that you can take with you. And so, I would almost throw that back to you, Flo. Like, how do you at Cardo, right, like ensure that the people on your teams are right, stable enough at Cardo, right, to or any other firm. It's not specific to Geo, right? But it's a difficult question because certainly no, you can't do this. Or I don't think I would have been able to just learn this on the weekends, right? So I spent like 6 months learning how to do this stuff.
Yeah, I think in the case of our data science team, we're often learning with our customers as well, and their problems are changing so much as well, particularly this year. We've been working with architecture firms in the US to plan their return to work inside buildings. This is a problem we've worked on before in airports and shopping centers, but it's not something we've worked on before in the context of offices. So really, and that's a big reason why we recruit out of academia into our data science team, so that we have people with very specific expertise in-house, like the team who presented yesterday.
What kind of thing are you doing in buildings? I didn't realize that you were doing that.
Yeah, well, there's a very big project in the airport industry, which is all about wayfinding between retail locations, gates, security, etc. But I shouldn't digress too much because I'm conscious of the time, Jamie. We could talk forever, I'm sure. I think we've got time for one more question. So Anita Gracer, I'm sorry about the pronunciation, has asked, what was the source of the GPS data? Was it one specific app or an aggregate collector?
So thanks originally goes to Cardo, who had supplied this data through Cardo, although it's a different firm than Cardo currently contracts with. The standard story for these apps is that there's a suite of software development kits that firms develop, either that people just install in their apps, or a larger app can sell bulk data. And so there are a number of firms, some of which, like I think Unicast is available through the Cardo platform. Is that right? So those firms will aggregate together many different sources of data and give you a larger and usually cleaner sample. And so that's usually what you're starting from.
Mm-hmm. Absolutely. Great, Jamie, there are more questions, but I think we should probably take them up on the chat or in the networking break later as we need to move to the next session. Thank you so much for joining us.
Thanks.